Hey everyone, sorry to make you wait. So I'm Ameet Talwalkar. I'm filling in today for Neil Conway. I am Chief Scientist at Determined AI and a Assistant Professor in the Machine Learning Department at CMU. So today I'm going to be talking about deep learning in practice. So I think everyone in this room has heard about the buzz surrounding deep learning and the impressive impact it's had over the last 5 years on a variety of applications, whether it's autonomous vehicles, or voice-powered assistants, or translating language. We've seen a lot of cool things that have been powered and really pushed forward via deep learning. And of course, we're kind of just scratching the surface. More and more people and organizations are starting to use deep learning for various kinds of applications, and it's really exciting to see what's going to happen next. But there's a bunch of problems with actually using deep learning in practice, and the two of the core problems are that it's complex and expensive to actually get deep learning applications off the ground. So in terms of things being complex, in order to actually get deep learning to work, you have to be an expert in a variety of things. You have to know about deep learning and machine learning. You have to understand underlying parallel and distributed systems. And of course, you also have to understand the data and the domain that you're working with. In terms of things being expensive, there's really not many people who have all of these expertise. And the very rare number of people who do are really hard to find, really expensive to keep. Beyond that, there's a computational issue in terms of expense. So GPUs are very expensive. They're kind of where everybody's running deep learning these days. They're also they're rapidly changing, so they depreciate very quickly. So both in terms of hardware and people, things are really expensive. So kind of to understand a little bit more what some of the core problems are in getting a deep learning application off the ground, let's consider what a canonical deep learning workflow looks like from the point of view of a deep learning engineer. So this is somebody who, I'm going to assume is already at an organization that's decided that they're pushing forward with deep learning. They already have an application in mind. What do they then need to do to go from that high-level application in mind to an actual product based on deep learning that they can deploy? So first, you need to collect data, from wherever, whatever data you can use to actually train this model. You also need to choose the deep learning architecture or the family of architectures that you want to use with your training data. And then, of course, you need to perform training. So there's multiple steps in training. The sort of core problem that you need to solve is actually training a particular model. This is problematic computationally. It can take days to train on a single GPU. This is something, you often see people downsampling or using simpler models to actually get a model trained in a reasonable amount of time. But training is more burdensome than just training a single model, as you have to tune the various knobs of these architectures. These architectures are pretty complex. Unfortunately, we don't really understand how they work and why they work. And as a result, there's a lot of tuning involved to actually get a model that gives you pretty good accuracy. And if it can take a day or a week to train a model, it can take weeks or more to search through the space of models and actually to get a good one. So searching through this design space is really expensive, and it's also itself a manual and opaque process. It's not really clear how to do this in a systematic and efficient way. Beyond that, this process isn't linear. It'd be great if you could start with data, collect a model, perform your training, and bam, you're done. But that's not really how things work. You go through this process once. You either find bugs or mistakes in your modeling assumptions, or if you're doing things well, you might come up with new insights in terms of how to better pre-process your data or better modeling assumptions to actually improve your downstream performance. So typically, you're refining and iterating and doing this over and over again. And then under the hood, there's a lot of additional pain points. So one involves data management, So first, this data that you're collecting, Deep learning is sort of one of the two big innovations in deep learning. This is a 30-year-old, if not more, set of technology. It's that we have more computing and we have more data. So fundamentally, we want to be leveraging these really large data sets when training, and getting them into the system where we actually want to do the training can be expensive and painful. Second, there's crucial experimental metadata that may or may not be being captured right now. And this is both metadata involved in keeping track of the intermediate results of the different models that you're training. This is useful for debugging and for innovating and visualizing what's going on. So it's important for refining and iterating. There's also, though, just the capturing exactly what you did for reproducibility purposes. What software did I use? What version of my data? What version of my code? What version of TensorFlow? Whatever. So that 6 months from now, when you have to reproduce that result, you can actually do that. Oftentimes, this data either isn't captured, or if it is, it's captured in a series of logs, and the ML engineer is left to write shell scripts and parse through this stuff themselves. Then we get to this topic of cluster management. So what we've experienced is that the majority of customers and folks that we've talked to, they have invested significantly in on-prem hardware to actually, for their deep learning applications. Yet the solutions that they currently have for actually managing this hardware are not so great. So one solution we've seen a bunch is that there might be a team of 10 ML engineers, and each one of them owns, quote unquote, owns some of the GPUs. So they're idle a lot of the time. Alternatively, a more sophisticated technique that we've seen is that there's a shared spreadsheet where the different users can check off the different machines that they're using. And in general, the point is that this hardware is really expensive and it's often underutilized. Not having a good way to orchestrate this hardware also means that more sophisticated and advanced things that you might want to do, for instance, parallel training of an individual model, become really difficult. All right, so what I've talked about so far is all what you do at training time to go from a data to a model that has reasonably or good enough accuracy for your application in mind. But then there's also deployment considerations, and these are often at this point a secondary factor, even though they're super important. At the end of the day, you can have a really highly accurate model, but if it doesn't fit on your phone or whatever other edge device that you have, or if the latency is too large to actually serve queries, then it's not actually useful for the application that you have in mind. But oftentimes these SLAs are ignored during training, and after the fact, people are trying to fit a square into a circle. And this is sort of some of the, I guess, what you were asking me about was more about interpretability, but in terms of pruning these models and trying to fit them into phones, this is often one of these ad hoc processes people do after the fact. And beyond that, right, there's also issues of deployment of, how do I monitor to figure out when I need to retrain, how do I redeploy, that sort of stuff. Right, so deployment's also a real challenge for people. What I want to talk about today, though, mostly is recent research that I've been looking at focused on training, both in terms of training individual models and in hyperparameter tuning. So the first thing I'm going to talk about is recent work related to hyperparameter tuning. It's this algorithm called Hyperband. It's joint work with a bunch of collaborators, including my student, Leisha Lee. And to motivate this problem of hyperparameter optimization, there's a recent paper by folks at Google where there's a research paper where they report they report the results for a particular application, which is an English to German translation task. And as part of tuning the knobs of the models that they want to use on their data, they require 250,000 GPU hours. So translating that back to, say, EC2, that's $250,000 for a single paper for a single application. So this is really expensive, right? So there's real questions of, can we do this faster or more cheaply? And also, can we get better results ideally while doing so? So I'm going to briefly make sure we're all on the same page about what we're trying to do with hyperparameter optimization, and then present a new method that we have that moves things forward. Right. So consider this very canonical problem of multi-class classification. You have a bunch of images. This is the MNIST data set. It's very old, but people like to use it. Right. The goal is just to predict, given a new image, whether it's a 0 through a 9. Okay. And imagine we want to use some family of deep learning models to make to learn a model to make these predictions. Right, so the first thing we're going to do is, we don't just pick a model, we pick a family of models which determines this model space or a set of hyperparameters that we want to tune. Right, in this case, in this example, there's 4 knobs that we want to tune. In more practical applications, you can have dozens of knobs. This is kind of a simplistic example. But once you define this problem and you want to search through these hyperparameters, this hyperparameter space, what do you do? Well, the typical thing that people do is that you just, you try a particular hyperparameter configuration from the space, and then you take that configuration along with your training data, feed it into some black box solver that's running, gradient descent or stochastic gradient descent, and then you get some trained model, and then you want to evaluate it. So you can evaluate that model on some held out data where you know the answers to the predictions, and you get some score, predictive error associated with this particular configuration. But now, of course, you don't do this once. You're doing this over and over and over again until you run out of money, you run out of time, you get bored, whatever, until you need to give an answer to your boss. And at the end of the day, you take all these configurations, each one of them corresponding to a trained model, and you pick the one that's the best, the one with the lowest error. So in this toy example, that's this guy here. So the problem that we're looking at and that we studied was how can we efficiently identify high quality hyperparameters. So by efficiency, that means resources consumed, and really that just means how fast it takes or how many machine resources we need to go through this search process. And then in terms of quality, we want to find a model with low predictive error. All right, so what do people currently do today? So what was the state of the art before we started working on this stuff? Well, sort of the canonical baseline is random search, and it works surprisingly well. The idea, as it sounds, is that here's a picture of a 2-dimensional search space. So there's 2 knobs to tune. This is a heat map where the red circles correspond to good areas in this heat map. So ideally, you want to find a configuration that's in one of these red circles. And what you do in random search is what it sounds like. You just try you randomly search through the space, And the hope is that if you've sampled enough points, one of them will be within or close enough to one of these hotspots that you'll get a good model. Great. More recently, people have thought about more adaptive methods for hyperparameter optimization. These are also called Bayesian optimization methods. And the idea here is that you first start by doing some random search. You coarsely search through the space. But once you've done that, instead of continuing to just randomly search for new points or randomly picking new points, you use what you've seen before in the past to guide your future search. So if things are going well, you sequentially keep picking new points. And like in this example, this is a positive example. The subsequent points are all clustered around these two hotspots because intuitively you're able to learn from what you've seen before and get a sense of where you want to look next. Right? So these seem like reasonable approaches. To understand when they work and when they don't work, let's assume that we have a space of d hyperparameters. So in this case, this is just d equals 2. We have 2 hyperparameters. And that we have a budget to consider n hyperparameter configurations. Or in other words, we have a budget to train n models. So here n is just the number of points we have here, which is what, 15 or 16. Right, so in one case, we can consider a case where the number of configurations that we can look at is a lot more than the number of hyperparameters we have. So imagine here, d equals 2 and n equals 100. So what exponential means is, roughly, n is exponential in d. So n is a lot bigger than d. If we're in that case, right, it seems reasonable that we can sample enough such that one of our, at least one of the points is going to be close to an optimal point. We can cover the space. If we can cover the space, then in other words, if we can get a coarse sense of how the space looks, it also makes sense to be adaptive and to subsequently learn or to use information that we've seen in the past to learn subsequent points to select. The problem is, right, there's this other setting where n is linear in d. So this could be, more like a deep learning setting. So now d is not 2, but maybe it's 10 or 20. And n, because it could take, say a day or a week to train a model, you're training 100 models instead of 1,000 models. So if n is 100 or n is 50 and d is 15 or 20, now you're kind of in trouble. So now we can't cover the space. Mathematically, there's this curse of dimensionality. The volume of the space grows much faster. It goes exponentially in the number of dimensions of that space. So we can't cover the space, which means that we need a lot of points before we can hope that every one of our points is close to, before we can cover the space. If we can't cover the space, that means we can't get a good sense of what different areas look like. It doesn't really make sense to be adaptive in the space either. So this adaptive method just doesn't really work either. And again, this really is the regime that we're in when we're looking at deep learning, just given the size of a search space and how expensive it is to train each model. Right, so what do we do? Right, we're stuck with a particular budget, right? Something like n hyperparameter configurations. We're stuck with a search space that we want to use. So a natural idea is we can use downsampling to, instead of training models all the way, let's somehow partially train models and effectively increase the number of configurations that we can look at. Right, so what exactly can we downsample? How do we take advantage of this downsampling to effectively look at more configurations on the same budget? Well, the intuitive idea that we've explored is this idea of taking advantage of the fact that learning algorithms are iterative. Right? So stochastic gradient descent is sort of the workhorse of most large-scale machine learning algorithms, including training deep learning models. And we know that it's iterative. So what does that mean? Right? So we can downsample iterations of a learning algorithm. So here on the x-axis here, we have a number of iterations. And on the y-axis, we have some predictive error. So this is just for a toy set of models. But the idea here is that each line corresponds to a different configuration. And our goal at the end of the day is to pick the configuration that's the best, right? The one that converges to the lowest predictive error. That's this problem of hyperparameter optimization. But the intuition here is that, right, if at the end of the day what we care about is finding the one best model, we don't really care what these guys actually converge to. As soon as we know that they're not going to be contenders and that we can rule them out, it's sort of a waste to continue to train them to their suboptimal, whatever they're going to converge to, because they're going to be something that we don't want anyway. Instead, what we really care about is of the models or the configurations that we're looking at that all seem to possibly be contenders, we want to focus our efforts there to find out which is really the best. So it's sort of like a tournament in basketball. You start, the NCAA, you start with 64 teams, or I guess what, 68 or whatever it is now. You start with a bunch of teams, and you want the best teams to compete at the end, and you throw out the other ones earlier. Similar sort of idea here. It's kind of like a tournament. The problem is, intuitively that's a really nice idea, but it's not so simple in practice, right? So the set of lines I showed you in the last slide were neat and clean. It was really clear which ones were going to do well. But what happens if the lines look like this, right? What happens if while you're training, the predictive error goes up and down, or it stays flat and then drops at the very end? How do you, right? These sequences can be non-monotonic, non-smooth, and there's this real question of how do we safely discard a configuration, right? Of course, if we train something and throw something out too quickly, maybe it was just a late bloomer, but it's going to be a really good configuration, but we threw it out too early. Alternatively, if we train for too long before throwing something out, we're kind of wasting our resources. So there's this question of how do you know when, without making really strong assumptions, to throw away a model and discard it. Right, so that's the focus of this algorithm that we've been developing the last several years. It's called hyperband. It's this novel downsampling approach. What I'll show you in the next few slides is we're able to achieve state-of-the-art empirical performance, which is nice using this downsampling-based approach. But what's also nice is that we're able to show that it's provably correct. And what I mean by provably correct is that we directly answer this question of how can we safely discard a configuration. We can show that provably you're not going to throw something out too soon. So I don't have time to go into the details of the algorithm. I'm happy to talk to you guys about it offline if you have any questions. But I do want to show you a little bit about how it looks empirically, how it performs. Right, so here's an experiment tuning a neural network. This is a 4-layer CNN with 8 hyperparameters. It's an image recognition task. It's using the Safar 10 dataset, which is a common benchmark. On the x-axis here, we have number of iterations. So 50R here corresponds to the number of iterations required to train 50 models. So this is equivalent to n equals 50 here. And on the y-axis, we have the best predictive error that we've seen so far among all of the models that we've looked at. So first we looked at random search, and basically what this is saying is that the best error we've seen at this point is whatever this number is, and it keeps going down. We tried a bunch of different adaptive methods. We looked at a bunch of different data sets. For this particular data set, this algorithm called SMAC early was the one that looked the best. In other data sets, different adaptive methods worked better or worse. But roughly, we did see some benefit of using adaptive over random. But then this is what we see with hyperband. And there's a few things to point out. So first is that at 5R here, this is the number of iterations corresponding. So R again is the maximum amount we're training any one model. So 5R means that we've used a budget to train the budget equivalent of training 5 models. So at this point here on the x-axis, the adaptive method and the random method have trained exactly 5 models because they're training every configuration that they look at, they're training it completely, which is basically allocating a number of iterations equal to R. In contrast, hyperband with this amount of budget, because it's extensively relying on downsampling, has considered 256 configurations. It hasn't trained any of these models to completion. It's thrown a lot of them away really early. But the point is that it's been able to cover the space a lot better. And that's a key component to why it's able to make, it's able to find good models more quickly. So what we see is, across our data sets that, we're typically getting a 50x, if not more, speed up over random search. Rough 5 to 30x speed up, I'd say, over adaptive methods, depending on the data set. We often find that we converge to a lower final error than the adaptive method. Again, this is data set specific. But one thing we always find is that we have much lower variance. And what I mean by that is these experiments are all runs averaged over 10 trials of these experiments, right? And for random search and adaptive search, the error bars are really high, or really big, because random search could randomly get lucky on one trial and find a great configuration, or it could get unlucky and find nothing good. So it's really variable. The adaptive method is also highly variable. Whereas hyperband, because it's looking at so many more configurations, it's a much bigger sample size, and therefore the error bars are much lower. And in practice, you're going to be doing this hyperparameter search once, not 10 times. So it really matters that reproducibility, getting roughly the same result every time, really does matter. Right. So another thing we looked at, we have a bunch of variants of these experiments, but I'll show one more for time purposes, and it's answering this question of what if I'm really impatient. And what I mean by this is, imagine you're in a situation, as we talked about, where it takes a day or even a week to train a single model. Now, if it takes a day or a week to train a single model, and it takes 20 times longer to actually do this hyperparameter search because you have to train so many models, it's not really feasible to spend half a year tuning your models, right? But of course, what you kind of have access to often is parallel resources. So the question we want to ask is, how can we parallelize this search in such a way that if it takes, say, a day to train a model, we want to do the entire search in 2 days. And of course, with random search, you could naively train. If you want to train 10,000 models, you can just run on 10,000 machines and they'll all be done in a day. But it's often the case that even if you're at Google, acquiring 10,000 machines is non-trivial. So the idea is that the number of configurations that you're going to want to look at, even if you're at a large company, is likely going to be much more than the number of parallel resources that you have. So the idea is that you want to get an answer in roughly the same amount of time that it takes to train one model with maybe a large amount of parallel resources, but it's still a constrained number of parallel resources. So how does that look? I'll show you an experiment kind of demonstrating this idea. And this is work that we did in collaboration with folks at Google. It's on a residual network. It's again using the Safar 10 data set, but it's on a larger network with more hyperparameters. So 16 hyperparameters. X-axis, again, is time. Y-axis is predictive error, so lower is better. And the duration, the total time here, it takes 2 days to train a single model. And the total duration here, like the end of this x-axis, is the time is what? 1.6 times 48. So at the end of this point, all the models, in terms of wall clock time, will have had less than the time it takes to train 2 models serially. And so what we see here, we get some curve from random search. And again, what random search is doing, we're parallelizing over 50 workers. So by the end here, it's looked at what, 70 or so. Each model might take slightly different amounts of time to run, but it's maybe trained 70 models or so on these 50 workers. Hyperband has trained an order of magnitude more, and it converges much more quickly. What's the difference between this gap? It's a 3% error, which is might not sound like much, but for this particular network in this data set, Hyperband within less than 2 times the time it takes to train one model is able to get state-of-the-art accuracy for this particular problem, whereas random search is 3% is far from it. So that's the rough idea. And then what can we say theoretically, right? I mentioned that one nice property of this is having some heuristic downsampling method is fine, and in fact that's how we started working on this problem. We played around with the heuristic, it worked really well, and then we studied it more. But it is nice when working, when using some method to know that theoretically there's some guarantees that it's not going to break, or that there's some motivation theoretically behind why we want to use it. And so I'm not going to go into much detail at all about the theory beyond saying that we can frame this problem as a multi-arm bandit problem. And for those of you who don't know what that is, that's fine. Basically, we're studying problems of this following flavor. So multi-arm bandits is a common subset of problems in machine learning. But the best arm identification problem is this idea of an arm here is a different configuration or hyperparameter configuration or model that we're looking at. Given n such configurations, the question is how many resources are required to find the best of these n configurations. And so we can use this existing theoretical literature or theoretical infrastructure or machinery for the multi-arm bandit setting to study this problem and show that our algorithm Hyperband has a really attractive required budget that you need to find this best configuration. And the budget is much smaller than what you would need for, say, just vanilla random search. OK, any questions before I move on to the second? Yes?
Which hyperparameters are you searching through?
So it depends on the problem, but so some of them, high level, the sets of hyperparameters can either be related to the architecture itself. So for a particular node, what sort of nonlinearity am I using? Or different questions about the architecture itself, how many layers you have, or how many nodes you have in each layer, things like that. Okay. And then the regularization things. So things about the model itself are some of the knobs that you tune. The other set of hyperparameters are broadly related to the optimization algorithm that you're using.
So like the learning rate scheduling?
What learning rate schedule? Do I use SGD or do I use Atom or something, things like that. Yeah.
What's the reward?
What's the reward? Oh, you mean here?
Yeah.
Yeah, good. OK, so in this best arm identification problem, the reward here is just the validation error, right? So we train on a training test, and basically so each arm is a configuration. Pulling an arm involves allocating another iteration of training or some unit of training to that, and the reward you get is just the validation error. And the idea, the best arm is the arm that has the best it's validation accuracy, and the best arm is the one that has the highest validation accuracy. That make sense? And I should also note that a difference between so on one hand, we're leveraging the existing literature on multi-arm bandits, but one thing that's different about our work versus traditional bandit work is that typically you make some sort of stochastic assumption about the reward. That every arm, when you pull it and you get a reward, it's that reward is sampled from some ARM-specific distribution, and you assume that that there's some expected reward, things like that. In our case, that's not the case, right? Every time we're getting a reward, that reward is the validation accuracy or error of a partially trained model. And you know that the rewards are going to converge to, we assume that the models converge, that the training process converges. And so assuming that it converges, you know that your reward eventually is going to converge. But beforehand, it's a non-stochastic variant of a typical, of a typical problem people study. So it makes it a little different. Any other questions? Yeah.
So are there any assumptions here, like error decays?
Yeah, good. So the whole point, that's a great question. The whole point of our whole motivation behind this was to make as few assumptions as possible, for better or worse. Right? There had been previous work, more in the theoretical ML community, saying if I make certain assumptions about, and actually there's been various papers saying if I make certain assumptions about like how these different models can, or the rate at which they converge, and like or parametric assumptions on how these traces look for these different models, you can do something interesting. The problem is that there's no way to know. And even if you say that, okay, I think it's going to decay exponentially, and so the constants really matter. And those algorithms, when those assumptions work, great, you're doing well. When they don't work, your algorithm could do something completely arbitrary, and you have no idea what's going on. And there's no way to know a priori whether your assumptions are going to be violated. So in our work, the only assumption that we make, the only assumption is that every model we're training converges to something. Basically, it's not, we assume that eventually, if you train for long enough, the validation error is going to be, is going to converge, which just means that the optimization process is converging, which is a pretty weak assumption to make. That said, by making additional assumptions, you possibly could do better. So, but our whole point was to say this just works very cleanly and kind of generally. OK, so let me move to the second part of the talk. Right, so the second part of the talk is on this problem, or this performance model called PALEO. It's a performance model for deep neural networks. It's joint work with Heng Chi, who's a student at UCLA, and Evan Sparks, who's my co-founder and the CEO of Determined AI. And the motivation here is, right, so I'm not going to here be presenting a new algorithm, but it's more trying to understand the landscape of distributed training for deep neural networks, right? And I'm going to motivate this problem, I'm going to go back to this paper by folks at Google, this machine translation application that took $250,000 to develop the application. When talking about what they did, they say that one major drawback of current architectures is that they're expensive to train, typically requiring days to weeks of GPU time. So right, we already talked about this, it's really expensive to train. But in response to this, there's a natural thing you might think about, right? So we want to use deep learning. People have used parallel and distributed computing a bunch in machine learning in general. So why not put them together and see what happens, right? So if it takes a week, maybe if I use 100 GPUs, I can now get it down. If I get linear scaling, it could be a really fast problem. And that's what we often see for linear models and other simpler models when doing things in parallel on things like Spark Set. So can we do something similar for deep learning? So I myself thought pretty hard about this. I guess 3, maybe even 4 years ago now, working with Evan. We were working heavily on Spark and on MLlib, and we get this question. I get this question all the time of where's deep learning in Spark? Why don't you have a distributed algorithm for deep learning? So we looked into it. And at the time, AlexNet and GoogleNet were the 2 architectures that people were excited about. So before actually implementing anything, we wanted to do back-of-the-envelope calculations, kind of trying to estimate what we would expect our speedups could be. If we implemented things perfectly and super efficiently, given the underlying communication constraints on, say, EC2 and the computation requirements on given current GPUs at the time, what sort of speedups could we hope to get? And what we found were that the speedups were pretty modest. So we abandoned the project and decided to do other things. But fast forward the last 3-4 years, we've seen, and I haven't checked this since earlier this year, but as of earlier this year, there were at least 6 distributed deep learning libraries within Spark itself. Beyond Spark, there's a lot of interest in distributed deep learning in general. I think late last year, there were blog posts by both folks at Google and Amazon presenting really impressive speedups on 100 GPUs getting a 50x speedup, even better, nearly linear speedup on 128 GPUs. So, right, so we saw these blog posts and we were curious. We said, what did we get wrong? Why did we abandon this project when other people were able to do so well? What did we miss? So that motivated us to revisit this problem, and it led to PALEO. which is an analytical performance model to systematically study distributed deep learning, scalability, and performance. So I'll tell you a little bit, before I tell you details about how PALEO works, I want to motivate why we think this is an interesting tool. And to do that, let's consider this two-dimensional grid. On the x-axis here, you have computational platforms. So this could be the hardware you're using, the communication bandwidth you have across your machines, how much hardware you have. Do you have 10 GPUs, 100 GPUs, and how they're connected to each other. On this y-axis, this vertical axis, you have neural network architectures. So is it AlexNet or a ResNet or Inception, whatever layer specifications, as well as the different training algorithms you're using. What's the batch size? What's various other properties of the iterative algorithm you're using for training. So given this design space, there's a bunch of questions that we can ask. So the most naive question we can ask is we could say, all right, well, imagine I know I want to work on EC2 on 32 GPUs, and I want to train my data on AlexNet. How much time and money is required to perform this task? That's a pretty boring question, not that interesting, but I guess it'd be kind of cool if if you could use a performance model to tell you that answer immediately. Slightly more interesting though, imagine you know that AlexNet or any other architecture is really good for your application, but you're on EC2, so you're flexible in terms of how much hardware you want to use. And you want to know what's the best bang for my buck. So given a fixed architecture, what platform should I use? That's a more reasonable question. An equally reasonable question is that you're a company, you just spent $500,000 on GPUs, you're stuck with that hardware, that's what you need to use. And at the end of the day, your goal is to get good accuracy on a particular application. You don't really care if you're using AlexNet or Inception or any other model, but you want to know for a fixed platform, which architecture might be most efficient for me. Another reasonable question. And then kind of the most general question is, can we systematically explore this design space? So what we've seen so far is that research groups and companies have spent a lot of time and money evaluating particular points in this design space to show that, I can get speed ups or I can't. But it'd be really useful if you could use a performance model to, for free, get a fairly good estimate of where are the interesting points in this design space and where we should focus more of our energy and interest. Right, so that's sort of the motivation behind PALEO and why we think it can be useful. So how does it work? So the high-level strategy is that what we observed is that a neural network architecture provides a declarative specification of the required computation. So what are you doing? You have a bunch of layers. At each of these layers, you're doing adds and multiplies. You're also then communicating different things across layers. So basically, we can map the computation and the communication to a specific choice of computational platform. So the picture is really easy. You tell me what architecture you have, say AlexNet. You tell me what hardware you're using. I know how fast I know how fast a GPU can operate. I can map these two things to a certain amount of computation and communication. I can map both of these to an actual time estimate. Right? So that's the high-level idea. The details are a lot trickier, and Hang in particular, the student who worked on this, did the hard work here. But there's a bunch of low-level details that make this not so simple. I would say the most complicated aspect of things is that while the neural network gives you a declarative specification of the operations you need to perform, there's a bunch of different ways to actually execute these commands. So convolution is a good example of this. The convolution is a single operation, a conceptual operation, but there's several different ways to actually implement a convolution. And the most efficient choice for a convolution is a data-dependent and architecture-specific problem. So if you have a performance model that assumes that the convolution is always executed in a certain way, it's going to be really inaccurate. So figuring out the right low-level way to execute every operation is non-trivial. We also have to estimate network communication for model updates. We're in a distributed setting. We have to figure out, we focus on bulk synchronous systems, but we still have to figure out, do we have a one-to-all communication, a tree-based all-reduce, or various different ways to communicate across different networks. There's also this issue of taking into some slop factor you have to take into account. Of. Software doesn't really squeeze all the juice out of its associated hardware. If you want good estimates, you have to take that into account. So I'm not going to go into details of how the performance model works. I encourage you to check out our paper if you're interested in more details. But I do want to show you a little bit, what sort of results that we get. So the first thing we looked at was, Evan and I going back to ourselves 4 years ago when we decided not to look at this problem in the context of Spark. We wanted to revisit that and see if we could verify what we saw before. So here, and I should note these are all simulations. We're not actually running any experiments here. We're just feeding information into Paleo and getting predictions of how long it would take to run various experiments. So this is a strong scaling experiment on simulating running AlexNet on EC2. Right, so we fix the batch. So the idea of strong scaling is that we fix the batch size as we scale to more and more workers. The benefit of this is that if you have a strong scaling experiment and you assume synchronous updates, then you're basically training the same model in a distributed setting as you would if you train on a single machine. Right? This is also, though, a challenging setting because it means that as you have more and more, right, if batch sizes usually aren't so large for deep learning, and so as you have more and more machines, you're basically doing less and less work per machine before you need to communicate. So it kind of makes sense if this is a harder setting, but it is actually, in some sense, the most fair setting because you're comparing apples to apples. So we assumed, we did these simulations assuming that we were using 128 K80s, using sort of standard assumptions about EC2, also using a batch size that's fairly large. This is beneficial to distributed settings. And here are the results that we saw. So x-axis is the number of workers. The y-axis is the speedup, the estimated speedup that we saw. And this is for 3 different variants of allReduce. 3 different variants of allReduce. And what we see is it kind of matches what we saw before. At best, when using 32 machines, we get a 5x speedup. And things actually get worse as you use more workers, according to Paleo's estimates, because communication really just dominates. Right, we then wanted to run a similar experiment, but now assuming weak scaling. So the idea here is that we assume a constant workload per worker. So as you scale to more and more machines, you're still doing the same amount of work per machine. So the overall batch size increases with the number of workers. We use a similar setup here, same setup as before, except again now the batch size, instead of being fixed, it's fixed per worker. So every worker as you add on is processing 32 data points before sending a message back to the master. And in this setting, we get much better results. So we get, for the best, the most efficient communication scheme that we're modeling, we get nearly 100. We get over 100x speed up at 100 when we're looking at 128 workers. The key point, though, here is that the workload is changing. This is not solving the same problem as training a deep learning model on, a much smaller batch size, which is what people typically do in practice. So, on its own, this is a very misleading result because who knows whether this model is actually something you care about. You can train it. It scales really well in terms of parallelism, but it might not be the model you actually care about. So, right, so that, to some extent, in my mind, this to some extent gave us an inkling of how we can reconcile what we saw before. We were focusing on strong scaling versus these new results, which presented, really nice speedups, but they were focused on this weak scaling idea. And again, I should note all of these are estimates. We haven't actually run any experiments. So there's no reason yet that you should believe that any of these estimates are reasonable, and we didn't either. And as a result, what we next did was we wanted to use Paleo to try to reproduce some results that we had seen in the literature to see if we can get reasonable estimates. So first, we looked at the TensorFlow blog post from 2016. We followed the same assumptions that they use in their actual experiments. And here are the results that we get. So we get similar scalability results, which is encouraging. There is one caveat here, which is that they're using an asynchronous parameter server to communicate. We're assuming synchronous updates. That said, we're clearly in the same ballpark as they are. And in terms of, this is just scalability results. In terms of raw wall clock estimate times, we're also within roughly 10% per iteration as what they report. There's a second, we have a bunch of results in the paper, but just as a second one is this one weird trick paper. This is actually a parallel setting, not a distributed setting. They have this really cool idea where they say for a convolutional neural network, instead of being only data parallel or only model parallel, you kind of want to be both, depending on where in the network you are. I won't go into details, but the idea is that they have 2 different types of parallelism. And we're able to model this using, again, the same setup that they use. These are the results, cut and pasted from their paper. They get really nice speedups on up to 8 workers. Again, this is a parallel setting, but they get over a 6x speedup on 8 workers, which is nice. Paleo, we're very, very close, both in terms of wall clock time and speedups. One other interesting thing though to note is that the key point of his paper was to talk about hybrid parallelism and say, hey, it's better than just vanilla data parallelism always. But they don't actually do a benchmark to compare the speed up between this one weird trick idea and just a vanilla data parallel method. But with Paleo, it's really easy. It's just changing one input. So we can simulate what we think data parallelism would look like. And we can compare the results. And we see that you go from an estimate of 6.7 speed up to a 5.4x speed up. And so this is one simple illustration of how something like Paleo can be useful to search this design space very quickly. Right, so what are the takeaways from PALEO? One, what is it? It's a performance model that can efficiently and accurately explore the design space of architectures and computing platforms. Second, right, I would caution you to, when looking at scalability results for deep learning, to consider strong versus weak scaling, and more generally, just ask about accuracy results, not just time results. Right? You want to make sure that the final accuracy is actually reported and matches what you would have gotten on a serial machine. I would also note, though, that I don't think that PALEO is a negative result. I think it's an interesting tool to search this design space, and what we really need are new architectures or learning methods that have more favorable computation or communication profiles. We've started to see this a little bit. Facebook had a paper where they do report accuracy results and show that they can train ImageNet in an hour or something like that, and there's been some follow-up since. So I think people are moving in the right direction here. But the point is that it's sort of non-trivial to train deep learning models in a distributed fashion with a large number of machines. If you're interested in trying this yourself, Hang made this really cool website where you can toggle the different parameters and get in real time different scalability results. So that's kind of cool. Right, so I'm pretty much done. Just to step back for a second. Right, I talked mostly about this training process. I think both in research and industry, moving forward, there's a lot of work to do to help people, and I would consider myself more to be in this camp. Right, I like collecting data, choosing the architecture, and doing the modeling stuff. I find this stuff to be harder. Right, that my background's more in ML, less in systems, and I think there's a lot more work to do, not just on training, but on all these other components to actually make things a lot easier for ML engineers. So with that, I'll conclude. We're hiring at Determined. Need to plug that. I'll also plug, I'm co-organizing a conference, an academic conference on SysML to target this community of the intersection of machine learning and systems. First conference is going to be at Stanford in February. If you're interested, you should check out the website. All right, thank you.